We can solve systems that are represented as augmented matrices using row operations. And our goal when using the row operations is to achieve a matrix that shows the solution. That means that there are ones down the diagonal and zeros elsewhere in the left portion of the matrix, and that there are like answer numbers on the right side of the matrix. So example 1 shows a matrix that has exactly one solution that is completely solved. The way that we write the solution from a matrix that looks like this, so this matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1 on the left side, and then on the right side, 2 7ths, -6, and 1 are the answers. The first column is x, second column is y, third column is z. So the answer in the first column is 2 7ths. And now if we were to take this matrix and just write the answer, we would have 1x, so just x, plus 0y, so plus 0 equals 2 7ths. So you can see we're left with the answer x equals 2 7ths. So when there are zeros elsewhere in the matrix, that means that we have that single variable solved for. When there are zeros elsewhere in the row for the other variables. So the second row, x is 0, y has coefficient 1, z has coefficient 0, means that that second row tells us that y is equal to -6. And then the third row, x, y, and z, x and y coefficients are 0, z coefficient is 1, and then the answer is 1, tells us that the z is equal to 1. So the solution from this matrix is 2 7ths, -6, 1 as a coordinate solution. But now it might be possible that we cannot get the matrix into this form with ones down the diagonal and zeros elsewhere. In that case, we might have a situation where we have infinitely many solutions for the matrix, and there's a different way to write the solution in that case. So here's what that matrix might look like in example 2. On the left side, we have the matrix 1, 0, 4, 0, 1, -6, 0, 0, 0, and then we have answer numbers on the right side. So you can see that there are ones partially down the diagonal, but that the final row is all zeros. What that means is that through the solving, 2 of the rows ended up being the same, and when subtracted from each other, one of the rows gave all zeros. So here's what we do in that case. The first row, we have our x, y, and z, and then our answer. So let's set up that equation. 1x, so x, 0 y's, so no y's are needed, plus 4y equals 12. And then the second equation, x, y, and z, 0x, 1y, minus 6z equals 8. And then the third equation is all zeros, so we don't write that equation. So what that means is that the last variable z can be any number. Because z is the one variable where there's no 1 along that diagonal for z. So now the way that we write this solution is we'll set up our solution as we did before as a coordinate point. I'm going to leave a big spot for x, a big spot for y, and then z can be anything, so I'm just going to write z. And in the other parts of the coordinate point, we're going to have expressions solved for x and y. I'm sorry, there's a little error in the red equation. That should be 4z, not 4y, because the 4 was in the z column. Okay, so now we take these two expressions, the red one and the blue one, with x and z and y and z, and we're going to solve for x in the first one. So solving for x here means we'd subtract 4z from both sides to get x equals 12 minus 4z. And 12 minus 4z is what we write in the x-coordinate of the solution point. And then the y equation, we're going to do the same thing and solve for y, so that would mean adding 6z to both sides to get y equals 8 plus 6z. And that's what we write in the y-coordinate of the solution point. So whenever you have a missing one along the diagonal and that whole row is zeros, that means that that variable can be any real number. So in this case, z can be any real number, so we just write z as that point in the coordinate point. And then the other variables, we will have expressions in terms of that variable. So we end up with this parametrized solution of infinitely many solutions.